About a 3-minute delay. Hey guys! Right, so I'm just gonna quickly mute my other YouTube window. Just mute that one. Gonna come up any second. There it is. Right, mute that one. So that's now running. I think if you can change the quality of it to make it so you can see my screen a bit better. Right, today's lesson, folks. We had 2 learning objectives. I need you guys to know the stages in the mass spec machine and understand the M over Z value. That's all I want to do today. M over Z, lowercase m. There you go. Cool value. Right, now at this point, I'm gonna set my laptop up so I can write on it. Boom. I'll also plug it in so that way it doesn't die. I haven't got my good microphone. I haven't got Harry's good microphone plugged in. I've been using it all day and I've left it. It's in my bag, I think. No, it's okay. Right, okay, guys. So last lesson, we started the process of looking at atomic structure. Whoa. Sorry, guys. Yeah. Last lesson, we started looking at atomic structure. Can you
share your screen, please?
Oh, yes, thank you. Thank you. Thanks, guys. See how useful it is having you on the chat? Eh? Otherwise, I would have been chatting for ages. There we go. Okay, yeah, so these are what we covered last lesson. We recapped atomic structure. We talked about the idea of where everything was, masses in grams, and also relative. We also came across all of our definitions: mass number, atomic number, relative atomic mass, relative molecular mass, isotopes. We came across all these. And then we talked about the examples of isotopes which you guys need to know. You must know chlorine. I cannot stress the importance of knowing her. Yeah, that comes up regularly on your Unit 1 paper, and you must. You should see the last one that was on the January paper, man. It was tough. They did a really clever trick. It was mean, but you had to know your chlorine because you had to draw your graphs. Okay, so today's lesson is what's called mass spectrometry. So first thing I need to note down is number 1. This is where I need to make sure I've got all my things working. Okay, so number 1, what is this device? I think the pen's going to be too thick, but I'll stick with it. The mass spectrometer, the mass spectrometer is a device used to measure particles, to measure a particle's abundance. Change my color. Please note I've changed my color. Abundance. First question on the chat. Are going to do question 7 to 10 of all sorts. No, I'm not going to do that in today's lesson, Ange. I'll do it some other time. I'll go through the homework some other time. I will go through it though. I'll do that next time. Abundance, first question on the chat. Guys, what does the word abundance mean? Yeah, so to measure a particle's abundance and mass over charge value, M over Z, and M over Z value. Right, I'm going to quickly explain this one. So this is the same as mass over charge value. So the lowercase m is mass, of course, and charge is Z. Yeah, the charge is Z. Okay, so anyone on the chat, please, for abundance? If people don't know what abundance is, please write on the chat, no idea, and then I'll explain it. And I still need to get back used to dealing with the delay. So the word abundance. Any ideas, anybody? Okay, so the word abundance. The amount of, dot, dot, dot. So the amount of, quantity of. Yes, same thing. Well done, Aisha. Yes, quantity of, amount of, quantity of. I will also say, I'm tempted to mention the word ratio here. Yeah, so abundance is sometimes measured in terms of ratios because it's the amount of X in a whole. Yeah, the amount of X in a whole. So an example being, out of 100 particles, how common each isotope of an element is. Yes, absolutely, Louis, absolutely correct. Yeah, this idea of it, I love that answer actually is really, really nice, showing you how common that isotope is amongst others. Yeah, the amount of X in a whole. So, for example, if we had, I'm going to do EG at this point. I'm going to change my color back to black. EG, out of 100 atoms of chlorine, 100 atoms of chlorine, 75, I actually said 75, no, something different. 75 particles are blank, and 25 particles are blank. So I'm going to ask Anch this one. Anch, the 75 particles, who's it going to be? And then I'm going to ask Harry, who's going to be the 25 particles in chlorine example. I'll then put that down then into a ratio, yeah, which is commonly 3 to 1, and then we have the people who they are underneath. Yeah, so I wonder if people can remember who those people are. Ange, can you remember which ones there's more of in chlorine? I know that the delay is massive. I'll keep waiting. Okay, I'll leave those to have a chat there and have a think about it and spit out my answer in a minute. Okay, so abundance. So, okay, now the M over Z charge I will talk about in the context of the mass spectrometer. It'll make more sense. Okay. So we know that chat there and have a think about
CL35 over 17.
I like it. CL35. Oh, I shouldn't do that. I've got to do CL35. Thanks, Ange. CL35 and the 25 one, Harry, remember? I know that you guys talked at the same time. That's my fault. We know that. Oh, keep annoying me, you stupid thing. We know that all elements have.
I wasn't sure, sir. I mean, so I don't know.
Okay. Louis, we know that all elements have isotopes. How? So this is where I get to do a little bit of history in terms of mass spectrometry, trying to explain to you guys how exactly this was discovered. And I can do a little bit of, I've got some old files here, which is quite nice. This is me going back in time to way, way, way earlier lessons. So if I go to backups, pen drive, backups, teaching file, A-level, teaching file, AS, unit 1, atomic, physical chem, atomic structure, and then atomic structure, and then isotopes, and then this guy. So this is how old it goes. It's a bit crazy. Give me my laptop a minute. Struggling. Oh, some can be converted. Oh, no way. No, no, no. It's saying it can't do it. Notebook Interactive was unable to convert some files. The legacy notebook file converter failed. Oh, man. That's the end of that lesson. Wowzer. I'll have to Google it. Oh, man. First mass spec photo. That's not going to work, is it? Should do. 1921, I believe. Images. Oh, I can't remember who it was by either. Man, it's been a long time since I've looked at all these kind of things. Oh, man. Wow, look at the very Francis Aston 19. Oh, what was the year? Can't remember what the year is. Aston 1921. It was by Aston. It was indeed. Aston 90. It's like 1919 or something, or 1920 or 1917. Oh man, I'm gonna get the year wrong, and it's not gonna give me the photo. Oh man. He discovered the first isotope. If I go neon, because Aston was the one who discovered it, neon. Maybe that'll show the photo. Come on. Show me the photo. Oh, where is it? There's a photograph of his slide. I can't believe I've lost everything. I'll have to see if I can repair that file. I should be able to. Oh, it's going to take too long to do this. The internet at home just ain't as quick as the internet at school. Oh, that sucks. Okay, I'll skip on. So anyway, so Aston invented a device to be able to look at gases. That's what he was looking at. So 25 chlorine. Thanks, Louis. Good job. So if let's imagine. So how do we know that isotopes exist? So let's just take the example of chlorine. So we can just go, e.g., let's stick with, all right, well, we've seen chlorine 35 and 37. Let's use somebody else. Let's use bromine, e.g., bromine. Bromine exists as Br79 and Br81, two different isotopes. Here's what those particles look like. Here's the Br79, and here is the Br81. Now you can see I have deliberately made them different sizes. We know that the particles, that in reality, they're exactly the same size. Yeah, and I mean exactly, but one of them is heavier. So what we now need to do is we now need to separate these particles. Okay, so let's put a subtitle. Separating the subatomic. The subatomic. Okay, so if we want to take protons, neutrons, and electrons, see what I've done there? It's a little baby, tiny little electron. If we want to take these particles and we want to separate them, what we can do is we can do some neat tricks. So here is method number one. Method one. So method one is an electric field. Electric field. Let me show you why. If I take a proton, a neutron, and an electron, and I pass them through an electric field. So I'm going to create an electric field. Change my color, please do the same. My laptop's struggling a bit now at the minute, guys, which is interesting. Yeah, here's my my electric field. And I've generated that by having the top plate as the positive plate. Oh, my laptop's really slowing down now. So I don't know quite how to speed it up. I feel like it's because it's running something else in the background. Oh no, which it really shouldn't be. It's on full tilt as well. I feel like there's something going on here. Okay, I'll leave it there. I'm tempted just to scroll down my other, no, I won't. Okay, so this is the electric field. This plate is positive, this plate is negative. Now, when these particles go through the electric field, we can predict their path.
doing the same thing.
So I'm going to color code this. Let's send the positive proton through the field. I'm going to give you three options. Option number 1, option number 2, and option number 3. So 1, 2, and 3. Which one do you think, Josh, which path do you think the proton will take and why? Next, change my color. I'm going to go for the neutron, the neutral neutron. Path number 1. Path number 2. Path number 3. Don't know why I keep drawing the circle next door to it. I'm going to ask that to Louis. I'm going to go for the neutron, the neutral neutron. Oh, I don't know why my laptop's deciding to play my voice. That's because somebody else was playing it, weren't they? One of you guys was doing it. Yeah. Okay. Still waiting on Josh on the direction of the proton. Then let's do the electron. Josh has given up on me. Nice one, Josh. Okay, guys, so neutron option 2. Thank you, Louis. Absolutely correct. So the neutron now gains path number 2. It is unaffected by the electric field. It passes straight through. Josh, can you write on the chat, please? Ansh, what's the direction the electron's going to go? Right, I'll do options 1, 2, and 3. Come on, guys. I know the delay is massive. Okay, while you guys are doing that, I'm going to start work on the next method. Option 1. For the electron, yes, correct. Let's get rid of that. Josh is just ignoring me. Josh has just put a, is that meant to be a number 1, Josh? Just a question mark. Okay. So the proton is going to go via option number 3. It's cool to see that they're all different. Yeah. The proton is going to be attracted towards the negative. Which paths will the proton go? Yeah, it's going to go towards the negative, Harry. It's going to do that because we know that the electrostatic attraction is between oppositely charged particles. Well, the positive proton is going to be attracted towards the negative plate, so we'll move towards it, and it will also be repelled by the positive plate. The electron is the exact opposite. The electron is going to be attracted to the negative plate, to the positive plate and repelled from the negative. The neutron has no attraction at all and so passes straight through. So we can now separate these particles using an electric field. Now, just to actually mention, I'm just going to take this one extra step, because what I now need to mention is, let's look at this on a slightly grander scale. This is where my diagrams let me down. Right, and I just want to now talk about the two people that are being deflected. The positive proton and the baby electron. Right, do you know what? Let's put them side by side. Yeah, let's put them side by side. So the proton is going to be in red and the electron's going to be in blue because they're opposites of each other, complementary colors. And we're going to put these literally and have them run side by side with each other. This is just ridiculous how slow this thing's going. Right, so the path of the proton, if we make this top plate, we make this, oh, it's not what I want. If we make the top plate negative, don't know why it's doing this, and the bottom plate positive, we know that the positive proton, let's do the beam as a highlighter. Why not? Really struggling. Let's try that. Right. Here's the proton beam. Yeah, the proton beam looks like that. it gets deflected. I mean, in reality, it's actually more than that. As it enters it, and as soon as it starts to be, as soon as it enters that field, we're going to start to see its deflection. Yeah. Now the electron, on the other hand, the electron, that path is going to be very different. It's going to be like this. Yeah. The electron is going to get deflected a huge amount more. Would someone like to tell me why the electron is deflected so much more than the proton? Electron deflection is much greater than proton. The question is why? The answer is mass. The answer is inertia. So we know that the proton, the mass of a proton, we can, by the way, this is, it's because the mass of the electron is lower than the mass of the proton. Well done, Harry, spot on. So we have the proton has a charge, proton has a charge, brackets Z, of +1, and a mass, now I hope you guys recognize this. Yeah, if I do relative mass, yeah, we can just call it as a relative, let's do relative mass. A relative mass of 1. So it's like, so here's the thing, both charge and mass will affect how a particle travels through that field. Because if I take that proton and I were to give it a 2+ charge, on the chat, what's going to happen to its deflection? Would it be more, less, or the same? If I increase the charge is Z, looks like 2, that has a charge, brackets Z of +1 and a relative mass of 1. Whereas an electron has a charge Z of -1. It's the exact polar opposite, but the same but opposite, more. Well done, Louis, thank you. Yeah, but its mass and relative mass is tiny, is 1/1836. This is where I need a calculator to give me that number. I don't know where my calculator is. Oh, I've left it at school. No! I left it at school. That would be a disaster because I can't go back into school now. I've left my calculator at school. Can you believe it? For one time, I need my calculator and I've left it at school. And I can't have it for 2 weeks now. That is a total fiasco. Sanity. I'm going to have to use my horrible phone. Don't ever use your phones for doing calculator stuff. 1 divided by 1836 gives me a relative mass of 0.0000545. There we go. It's tiny. What that means is because the mass is so low, this is the equivalent of, you know, if someone throws, it's the ability to deflect something. The lighter an object is, the less inertia, the less momentum it has, the more easily deflected it is. And so the mass and charge both matter. So the electron has a much greater deflection than the proton does. We'll come back to that later. Right, method number 2. Method number 2. Method 2 is a magnetic field. It's to use a magnetic field. Please do not say use a magnet. Yeah, it's a magnetic field that is able to deflect it. This is where I have to do an amazing diagram now. So I need a magnet. I'm going to create a magnet. Oh, skillful artistry going on here, folks. Hope you appreciate this. There we go. Got a curved magnet. Check that out. So at this end, this is the north pole of the magnet. This is the south pole of a magnet. So I've bent. What I've done is I've created a U-shaped magnet. I think Yi Hearn is looking at my diagram going, yeah, I can draw better than that. I actually agree with you. Yeah. That's slightly better. There we go. Just about. Okay, so what we're now going to do is we're now technically you don't really need to do this, by the way. I'm just being fancy. Let's send in our proton again. So here's our proton, and I'm going to send the beam in. Let's make the beam nice and wide. Yeah. What will happen is it will be deflected by Fleming's left. So if we do the electron, yeah, but it will also be deflected more. I'm tempted. That's what I should have done. Is I should have done the proton on that side. Yeah, the proton on that side. That doesn't look right, you see now. What I should have done is I should have flipped those over. I'm going to flip them over. This is me not planning enough when I'm drawing diagrams like this. So the electron. No, I've done it again. Oh, come on, tablet. Yeah, there goes the electron, and the proton's deflection far less. Blimey, laptop's really struggling. Proton. Yeah, there we go. So we can manipulate subatomic particles. We can't deflect the neutron. Again, neutron will just pass straight through, unaffected by the field. This is where I need to put the neutron dead in the middle of these two. There we go, unaffected. So this is the neutron, this is the proton, this is the electron. Cool. So we can you don't need to worry about in terms of the Fleming's left-hand rule and all that jazz. It's just you need an understanding that we can manipulate charged particles with both electric and magnetic fields. Okay. So just out of just fun and games now. Okay, what I'd like you now to do, guys, let's go back to black. Right, I'm going to give you just question number 1. I'm going to give you an electric field. I'm going to give you 3 particles. Particle. This is particle number 1. Now this particle, I'm going to tell you, this has a mass of 15. A mass of 15. And is +1. Particle number 2. This has a mass of 3 and a charge of I've not done this very well. I want to rank up the charge of that one. I'm going to do charge of +4, and then oh no, I should make it easy for beginning with. Okay, so +1 and +1. Right. Let's make this top bit positive and the bottom bit negative. Right. On your notes, please, draw the path. Do it in pencil in case you get it wrong. Draw it in pencil. Draw the paths of the 2 particles of what you and how they compare. Doesn't have to be accurate. It's not about accuracy. This is about understanding and predicting flight paths. Flight paths. You can pause the video at this stage, and then as soon as you're done, unpause it, and you can have a look. Okay, so this one, it is deflected, but not by an awful lot. This one is going to be deflected a packet load, way more than the other one. The reason being has, in this case, greater deflection due to smaller mass. Okay. Question number 2. Move that up a bit. Q2. Electric field. Positive, negative. Going to have particle. Going to make this 8. Going to make this one 4. This one I'm going to make +2. And this one is going to be +1. Right. This is stretch and challenge, folks. Right. I want you to take your time over this one. Think about what their paths would look like. You need to consider that one is heavier. Yeah. If it is heavier, it would deflect less. But the higher the charge, the more deflection. So we've now got 2 things going on here. I shouldn't have done that, should I? In fact, I changed my mind. There's 8 and +1. Do that one first. This one is just about charge. Yeah? Draw the 2 paths. Pause the video, draw the paths, and then unpause to check. So, path number 1. Path number 2. Yeah. So this one, I've just done in the wrong directions. Oh, come on, Mr. Duncan. Come on. Oh, my laptop is having a full meltdown at the minute, folks. Oh, my goodness. It's struggling. Right. Sorry, I went the wrong way. Like that. There we go. Those are the 2 paths. So this time, I am purely looking at charge. It's nice, they both have the same mass, but the higher the charge, the greater the deflection. Make sense? Right. Now let's go back to that previous one. Question 3. Particle 8. I've gone massive and I don't know why. 8, 2 plus, and 4 plus 1. What would this now look like? I've made the lines of these too long, by the way. It's easier. So what would these guys look like? Pause the video. Unpause when you're ready. Right, this one's important. Their deflection is identical. Identical deflection. Why? The reason is m over z. We realized that both the mass and the charge of the particle affected their deflection. And what we realized we could do, okay, so we've had lots of really nice examples here. Going back over to this. The ratio of mass and charge, Z, the ratio of mass and charge, I don't know where my notes have all gone all wonky. Mass of a charge predicts deflection, overall deflection. Overall deflection. M over Z equals value, M over Z value. So for example, Cl plus 1, its mass is I'm going to do 35 plus 1. So I don't like doing that. I don't like that one. I'm just going like that. Yeah. So Cl, the m over z is mass is 30. I'm going to actually write this down as m over z equals 35 over 1. That's a z. Yeah, m over z value 35. Let's look at the next one. Let's go for magnesium plus 23. Mass 23 over 1 gives me an m over z value of 23. And everyone at this point is like going, I don't quite get this. What's the function of this? The function is when you get a 2 plus. 24, mg 24, 2 plus. What's its deflection going to be? 24 over 2. It has an m over z value of 12. Much greater deflection. Nota bene in red. Yeah? Nota bene. Bigger m over z value leads to less deflection. It's to less deflection. Okay, so now we understand that we can separate the subatomic, we can manipulate the subatomic, and we came to some decisions about how we can monitor this and measure it. Okay, so what's a mass spec device? Right. It's funny, my learning objectives have come out in reverse. Right. Mass spec. Spectrometer machine. Okay. Amazingly, this was invented in the early 1900s by a guy called Aston. And it is an amazing piece of kit, and it works incredibly well. There are currently a whole load of these wandering around on Mars, which is amazing. So, okay, here's how it does this. Here's how it works. Okay, so the machine is very, very straightforward. It looks like this. Number one, hang on. Number one, we have sample is being injected here, and this here, this piece of the machine is called the oven. Now, what the oven does, it's very straightforward. It turns the sample. So, for example, it'll take a sample and turn it into a gas. In order to be able to separate atoms, they must be gaseous. Otherwise, they're bound to each other. So, for example, magnesium solid would go in, and it would be turned into magnesium gas in the oven. Sometimes called the vaporization chamber. I'll add that there. Vaporizing chamber, sometimes called. Vaporizing chamber. Right, once it's a gas, the gas then runs through here. And this, by the way, is, do you know that the annoying thing is this part here isn't actually considered part of the machine. It's considered a separate machine itself, which is really irritating. It then passes into the main body of the device. And here's what the device looks like. There we go. What the device looks like. Okay. So it now enters chamber number 1. This is chamber number 1. Now, in this chamber, so you can imagine the gas particles are kind of trickling out here into this area through diffusion. And what it now comes, this is now called the ionization chamber. Ionization chamber. And in that is what is called an electron gun. This here is an electron gun. And it does exactly what it says on the tin. It fires high energy electrons across this gap. Like this. Now, what now happens is there are these electrons streaming across here. These are high energy electrons. Now, as soon as the atoms wander in to this pathway, they're going to get hit. Yeah, they're going to get hit by an electron. Here's the equation. So, ionization. We've seen vaporization, ionization. They are going to get hit by the electrons. So we've got magnesium gas. It's going to get smashed into by an electron, a high energy electron. And what's going to happen is this. This is where drawing stuff out is really cool. So here's what's happening. Magnesium atom gets hit by a high energy electron. And when it hits it, it's like being shot with a bullet. It's like if I was going to get Anch and stand there with his hand in the air, yeah? And I'm going to say, Anch, I'm going to shoot your hand with a bullet, and I want you to catch the bullet. There is no chance that's ever going to happen. What's going to happen is it's going to smash into the magnesium, and it's going to knock off another electron. This is ionization in a mass spec device. So I now have formed Mg2 plus gas and 2 electrons. Yeah. Here's the words for this. Describe the process. Question. Describe process of ionization in mass spec in MS. Electron gun fires high energy electrons at sample knocking off the outermost electron forming +1 ions. Right. So they've gone into this chamber, and all of a sudden the atoms now suddenly change. They go from being atoms to now they're ions. They get hit by an electron and they become positive ions. And by the way, they would actually shrink in size, but it doesn't really matter. They become positive ions. Now at this point, they enter chamber number 2. They enter chamber number 2. Chamber number 2 is called the acceleration chamber. Oh, come on, laptop, stop it. This is called the acceleration chamber. Okay, I shouldn't have written it there. This is called the acceleration chamber. Okay. What this now does is a rather neat thing. There are a series of plates. This is where I'm not drawing this very well. There are a series of plates inside this chamber. Now, these plates are negatively charged by 10,000 volts. These plates are negative 10,000 volts. Now, what this is going to do is it's going to attract the positive ions. Acceleration. Positive ions are attracted to the negative electric field. Now you'll notice that the plates have a gap in them. Now this does a really clever trick. What this does, it means when the particles pass through it, the only ones that make it through are the ones that are in a beam. So what this now does is not only does it accelerate them, but it then also turns them into a beam of positive ions, all traveling in the same direction. So it's focusing them, it accelerates them and focuses them into a beam. Positive ions are attracted to the negative electric field and focused into beam. Right. That's all you have to know about that. Okay. So now we've got a stream of particles all heading in this direction. But we know that each particle has a different mass. They're all +1. Now there will be, nota bene, every now and again, nota bene, every now and again, a +2 ion will be formed. Just gets hit twice by the gun. Yeah, will be formed. And that means it's going to change its deflection. That doesn't matter for now. But we now make these beams, and what we're now going to enter is a magnetic field. We've got a giant electromagnet generating a magnetic electromagnet that looks like magnetic electromagnet. Yeah, creating an electromagnetic, they're calling it a magnetic field. Here is now our mag field. Right. Now what's now going to happen is they're going to get deflected. Yeah, this is called deflection. This is now deflection. Positive ions enter magnetic field. Notice my change in color. Magnetic field is variable. This is the only part of the machine that's variable. How are we doing for time? Lesson's just finished. Particles with higher m/z values are deflected less. Cool. Right. So let's look at what that looks like. Looks like this. Right. 3 particles entering it. Yeah. And they're entering into this magnetic field. Now, what's going to happen The magnetic field is set on a strength. And what's going to happen is, number one, let's look at the tiny one. Let's choose the tiny one first. Come on, laptop. Right, here's the tiny one. Right, now what we're aiming for is to get it down here. So the little one didn't make it. The reason being is it was deflected too much. Let's look at the big one. That one wasn't deflected enough. So I don't see that one either. But what I now see is the medium one. Different particles get deflected a different amount, which means I can now detect each one individually. All I have to do is vary. Aren't they going in like a beam? Yes, they are, Ange. Literally like in a, it's okay. That's fair enough. Ange is critiquing my picture. Ange doesn't like my picture. Stuff you, Ange. Let's try this again. Okay. He doesn't like my putting them in like that. Let's put them in as, okay. So they're actually in this lovely, they're in a holding pattern. Yeah. So they're moving in this direction all together. Yeah. So let's do this guy in red. Let's do the light one in red. My laptop is really struggling now, folks. I can't even tell you why. It's just really struggling with it a bit. There we go. So we'll do this guy in red. So as he enters into the machine, he's deflected too much and we don't see it. The next one comes in, which I'm going to do then in blue. The next one, I'm going to do this one. This one's in blue. This one comes in and isn't deflected enough. And then the last one is, these are all queued up, remember? Yeah, they're all moving simultaneously. It's not like they're like bumping into each other. They're all in they're in a queue. And as one moves off one way, the other one's just going to get deflected more or less. Great smile, Ananch, great smile. Whereas the green one is the one that makes it right through. And we can vary the strength of this field. So you can do some rather clever bits with this. So now we need to talk about detection. Last stage in the mass spec device. Last stage, detection. Okay, so the positive ion. The positive ion strikes the detector. Strikes the detector. What does that look like? Looks like this. Detector, positive ion hits it. Boom. Now, when it does this, this detector is hooked up to a computer screen, and it is the negative connection. It is the negative connection from the battery. Now, what that means is, from a little screen perspective, if you're watching this, you can imagine this kind of screen. Yeah. So as soon as that positive ion hits that plate, the electrons that are all stacked up in this plate, one of them will get collected, and I will see a movement of my line. I'll get a little peak. So the positive ion strikes the detector. It gains an electron. Now that, from a physics perspective, gains an electron, causing a flow of current. Causing a flow of current. Yes? Now that current, is anyone in the room? Louis, how do you measure current? What device am I going to use? Gains an electron, causing a flow of current. The greater the current, the greater the abundance. If you have 100 ions strike the plate, you get a big flow of current. If you get 2 hit the plate, you only get a baby flow of current. The greater the current, the greater the abundance. An ammeter. Thanks, Louis. It is indeed an ammeter. This is hooked up to an ammeter, checking flow of current. So it's a really cool machine. Now, I know that I've overshot my lesson, and I apologize, guys. I just last thing I want to do the data. So what does the graph look like? This is really cool, this. So on the x-axis, here's the data it spits out, is abundance. Now, the cool thing is that's not really abundance, is it? It's actually amps. It's actually amps. It's current. They're measuring the amount of current, but they can, because current and abundance, because current and abundance is a straight line proportionality through the origin, we can just replace current with abundance. Oh, physicists. So we can just replace it. The next thing is m over z. Well, we're not actually measuring the m over z. What we're varying, remember, independence, what you change, dependence, what you measure. The independence on the x-axis, what are we changing? We're changing the strength of the magnetic field. But, so I have to go to the doctors, we'll finish the video later. Okay, Ange, no problem. So if the m over z is proportional to the strength of the magnetic field, we can put the m over z straight on the x-axis. So what now happens? Yeah, Ange, you go. Sorry, dude. I'm going to get told off for this, aren't I? So when you run this, you slowly turn up. So the m over z going from 0 to, let's say, go to 30. And we're going to put in magnesium. Magnesium has 2 isotopes, Mg24 and Mg25. Here's now what happens. As you apply the magnetic, as we increase the magnetic field, nothing is seen, because what's happening in the machine at low, here's what's happening in the machine at low Gauss. The Gauss is what magnetic field is measured in. So the particles are 24 and 25, plus 1, plus 1. So they're just hitting the wall. Yeah, that's all they're doing. 24 would actually have a greater deflection than the 25 would. But they just hit the wall. So we increase the magnetic field strength until 24 hits the plate. And what you get is at 24, you see a peak. And then at 25, then it disappears, because now 24 is overshooting the detector. And then at 25, you see a peak. And you can tell the abundance from the heights of the peaks and the m over z's, and you can calculate relative atomic mass. We'll pick this up next time. I'll bring it back to the classroom. I know I've kind of overshot there a little bit, guys, but it was worthwhile giving that extra a little bit. Right, guys, I'm going to leave you be today. It's been 58 minutes. I will see you guys all next lesson. Next lesson, we're going to start looking at the data, and then I'm going to give you some homework on using the data. I'll see you guys tomorrow. Bye, guys.